Hello, for today's video lecture we're going to be talking about area moments of inertia via integration. What is the area moment of inertia? The area moment of inertia, the area moments of inertia, as we're going to have multiple of them, are used in engineering mechanics courses to determine a body's resistance to bending or resistance to torsional loading. So these moments of inertia are second area moment integrals, and the moment integral about a specific axis represents that shape's resistance to a moment about that axis. So imagine we've got some circular rod, we make a cross section of the beam. If I could have a moment about x, y, or z axis, and if I have the moment of inertia about that respective axis, that kind of represents the resistance to the moment about that axis. So in all of this, Ixx and Iyy, or the moment of inertia about the x and y respectively, are going to be kind of in the plane of the cross section. So this red piece here is my cross section, x and y are in the plane, and the moment about x or y would be a bending moment. It would tend to bend this rod. The variable jzz is used for the area moment of inertia about the z-axis, and so a moment about the z-axis is different. It's not going to be bending. Instead, it's going to be torsion, and it will cause a twist in the rod. So we use I for resistance to bending, J for resistance to torsion. All right, so why do we have these second moment integrals as the resistance to bending, resistance to torsion? So the diagram above, we're going to start with bending. Diagram above shows a moment applied to a beam and the resulting internal stresses. So there's more later on that we can talk about here, but this is what the situation is going to look like. So imagine on one end we've got a bending moment. So this is the side view, this is the cross section. This is a bending moment about the x-axis. And to counteract that, I would have kind of this stress profile here. So in the center I've got zero stress, I've got compression on the top, I've got tension on the bottom, and it's kind of a linear relationship, 0 up and 0 down. All right, so the second moment integral is a measure of a shape's resistance to bending because we'll need to use the sum of internal stresses to counteract the moment, and number one, the further we move from the neutral axis, the moment arm, D, is going to go up, and then that goes up linearly with itself. And also, the further we go from the neutral axis, you'll notice the force goes up linearly as well. And so if the moment is a force times the distance, if the distance goes up and the force goes up, we need the second moment integral, or we're going to need d squared. The square of that distance represents the kind of resistance, how much it's going to counteract that initial moment there. All right, so starting from the basics, we've now talked about why it is a second moment integral. So I is the integral over the entire area, and we're doing it with regards to d squared. And so in this equation, we're going to be moving out from the neutral axis. So going up or down from the x-axis, or going left and right from the y-axis. And generally, we're going to set up mechanics problems so that the neutral axis is either horizontal or vertical, and the origin point is the centroid of the shape. So the centroid of the shape for both bending and torsion, that's going to be where we have that zero stress, that neutral axis that I'm talking about. All right, so if the neutral axis is the x-axis, we've got a horizontal axis. We're going to call that moment of inertia Ixx. If the neutral axis is the y-axis, we have a bending moment about the y-axis, we're going to call that Iyy. So these are not necessarily going to be the same number. So Ixx, Iyy are going to be separate numbers. We're going to take moments of inertia about each axis, and they would be different from the other moments of inertia. So for Ixx, the distance from the x-axis is actually going to be the y-coordinate of a point. So the further I go up or down from the x-axis, that's a vertical distance there. For Iyy, the y distance, or the distance from the y-axis for any point is just going to be the x-coordinate. So it's a horizontal distance left or right from the y-axis. And if y is at x equals 0, my x-coordinate is that distance. So this is a bit confusing because my distances for ixx are actually y values. My distances for iyy are actually x values. And so this leads to the following equations. So ixx is going to be going from some y min to y max. So I go bottom to top of the dA function times y squared. So we've got y in my x equation. So y min, y max, and y squared. Iyy is the opposite. So it's going from x min to x max. So it's going to go from the leftmost point to the rightmost point. And we're going to be integrating with respect to x in this one. All right, so what does this look like? So here is ixx, and what do I mean by these variables? So ixx is the moment of inertia about the x-axis, what we're solving for. Y min to y max, so this is the kind of bottommost y point to the topmost y point. So it's a definite integral. We've got kind of bounds on it. dA, this is just like we did for centroids. So as we go from the bottom up to the top, the rate at which the area changes is going to be equal to the width of the shape times the rate at which we're moving up. So the equation describing the width of the shape is going to be in terms of something times y, and then the rate at which we're moving up is simply dy. So now the dy winds up in here, and whatever this dA function is, the equation describing the width times dy, we multiply that by y squared, and that is what we are going to integrate in this. All right, so if we switch things up for iyy, so here we're going to be moving from left to right. So x min over to x max. And dA now, rather than being an equation describing the width of the shape at any one value of y, now it's going to be the height of the shape at any one value of x. So you'll need to come up with a mathematical function describing the height of the shape at any value of x, and you multiply that by dx, the rate at which we're moving left to right. That is the rate at which the area is changing. So that dA function will get multiplied by x squared, and we integrate that whole thing, solve the definite integral, and we'll get a number out for iyy here. All right, so that is ixx and iyy. That's the rectangular area moment of inertia. Next up, we're going to talk about the polar area moment of inertia and torsion. So the polar area moment of inertia, abbreviated as J, is the second polar area moment integral of that shape. And so this value is useful in that, again, it is the resistance to torsion for that shape, helping us understand torsional loads and the kind of angle of twist in a shaft. All right, so this is a diagram. Here we've got a torque applied to one side, and this is, again, kind of the internal stresses we would see in our system. So it's the same kind of deal with bending, where as we have the second moment integral because as we move out from the center, the further we move out from the neutral axis, the larger the moment arm, counteracting the stresses, but also the stresses themselves go up linearly. So that is why we have distance and then distance again. So distance squared is going to be important for my resistance to torsion. All right, so starting from the basics, the second area moment integral, this is our same equation that we had before. In this case, though, it's going to be a little different. So we're moving out from some axis, so it's not a horizontal or vertical axis. And really, in our cross-section, the z-axis is just a point. It is just the origin point, and we are kind of radiating out from that point. So the neutral axis is going to be the centroid. That's where our zero stress exists, and we move out from that point. All right, so for the z-axis, it's jzz, so about the z-axis. The distances, we move out from the central point in a circular pattern. And the distances then are going to be kind of a radius measured from the point. So we had x and y in our rectangular moments of inertia. Here for our polar mode of inertia, we're going to have r. All right, so this is the equation we're going to end up using. So we are going to go from some minimum radius to a maximum radius. Again, it's going to be dA, so the rate at which the area is changing, times r squared. All right, and so this is what everything in that integral calculation would be. So the moment of inertia about the neutral axis, JZZ, the polar moment of inertia, go from r min to r max. So if you have material at the center point, r min is simply going to be 0. R max in this case would be the outer radius of my circular area. dA is going to be the equation describing the circumference of the circle within the shape. And so in a circle, it's just going to be a circle all the way out as we radiate out. But if you had something like a square, parts of that circumference would be inside the shape, parts would be out. You'd have to make that difficult calculation if you're doing this via integration. And so the circumference times the rate at which we're radiating outward, dr, is going to be my rate of change of area. So the circumference equation, dA times dr, or dA, which includes the dr term, times r squared. I take the integral of that whole piece, and that's going to be my polar moment of inertia. All right, so that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.